did want to go ahead and talk about a couple more analog components, basically capacitors and inductors. And we're not going to go into a lot of detail about them. You learn a little bit about them in physics, and if you're really interested, you go take an electronics class and you'll learn a lot more about them. But I just want to give you an overview and maybe explain a little bit about how they come into chemical engineering. So capacitors are a way to store energy in an electric field. And you'll see that we've got a couple symbols down here, C3 and C4. The numbers aren't important. That's just what number they were on the little software program I was using. But the differences are this C4 has this little plus. That would be an electrolytic capacitor. You'll notice it's got this little bent plate here as well. And that means these have to be put in a certain order, where positive is one side and negative is another. And regular capacitors, you don't have to deal with that. So anyway, but capacitors store energy in an electric field, like I said, and they're measured in farads. And capacitor technology has gotten a lot better. It used to be a farad capacitor was the size of a bread box or something like that, something relatively large, and that's gotten smaller and smaller over the years as we've developed better dielectrics and better ways to package capacitors and so on. So that's a trend you'll continue to see. And I mentioned over here two physical configurations, meaning two different types. One, you can have these parallel plates, and you can imagine that as, let's see if I can draw on here. Oops. Can I draw on here? Let's see. Pointer options, pen. Yeah, so parallel plates looks exactly like that, so I'm about to waste a bunch of time drawing. Oh wow, there's parallel plates for you. Super parallel. I should have just left that alone. Anyway, the idea being that the charges build up on these, or maybe a positive builds up on this one and negative builds up on this one. And you can also have concentric cylinders, where if I was looking at the top, those are perfectly concentric too. That is like textbook definition. And maybe the positive charge is built up here and the negative built up here. Anyway, the bottom line is you've got some dielectric in between your two, either your two plates or your two cylinders. And we'll talk about that later on in the semester when we talk about filtering. For now, we're just going to deal with things in the direct current world, meaning that kind of what you've seen in physics class and you'll see in electrical theory. Later on, we'll talk about what happens if we start running a signal through there that alternates. But anyway, bottom line is a couple different configurations measured in farads and store energy in an electric field. And so what does all this mean? Well, once again, I've got this little 5-volt battery, let's say, and we've got a resistor here. It's not of any importance. I mean, it's of importance, but we don't care what the value is right now. And a capacitor over here. Now what happens is, if suddenly we have a time dependence in our circuit. So if I say time equals 0, we close this switch. Well, you start to have current flow through here. Well, we can plot a couple things here. I'm going to call this kind of like, we'll call it VC, and we'll call our current I. Okay, so our voltage across this capacitor ends up with time going up. In fact, I did that not very well. Sorry about that. Let me fix that. It was supposed to be an exponential, but I did it the wrong way. Can I erase? Get rid of that line. Sorry about that. Let's try that again. Anybody following at home and looking at these equations knows I'm lying right now. Okay. So that's V. This is T. Actually, it looks like that. Where as time goes to infinity, our voltage across our capacitor goes to, in this case, 5 volts. May not ever reach it, but it gets close, let's say, depending on our resistor value. Now, if we were to plot the current, which I'll change colors because I can do that. If I were to plot the current, we'll do it over here, where this is T, this is I. Current drops off really quickly, and eventually gets down and approaches 0. So basically, as time goes to infinity, I goes towards 0. And so basically what we're doing is, after we close this switch, we're basically charging this capacitor. So if we started with no charge, we close this, we start to charge this capacitor. Then eventually, if you can imagine this, if VC were to equal 5 volts, if this is 5 volts and this is 5 volts, no current's going to flow through there anymore. So that's why I goes to 0. And there's these equations. I have up here tau equals RC. This is what's known as the time constant. And you'll see it appear in these equations. And that has to do with how fast this charges and how fast it discharges as this time constant. And you can do things based on time constants, like at 1 time constant this, 2 time constants this. Normally we say something like 5 time constants is we're as charged as we're going to be. So just a little note, couple notes on that. And so I did the charge cycle already, so I kind of covered that part. Now the discharge cycle, so pretend we've charged this, T0 we've charged this capacitor, so at T0 we're now going to open this one. So no more 5 volts, but we're going to close this one. So what happens now is this current is 0. Nothing's happening over here because we've opened this circuit. But we let this one, say it charged and say it got to 5 volts. Now what's happening is we close this circuit. We have current flowing this direction. We'll call this I2. And we run into the same sort of thing where we basically are discharging this current through this resistor. And initially that current's going to be high, and it's going to drop off. I and T. Because we have a big potential to begin with, 5 volts. And remember, this is just storing energy. And so as we discharge that current, we're like, I wouldn't say we're using it up, we're basically dissipating a bunch of it as heat in this resistor. And so the current drops off, and that's basically what we have. Okay, so that's a capacitor. Oh, there's this great analogy with an air tank, and I stole it from these folks. But basically, if you have a pump and a valve, and you're pumping air into this air tank, when this air tank is empty, the pressure in the tank is really easy to increase. But then as this tank gets full, the pump has to work a lot harder, and we get this die off here, and we reach our maximum. Basically, the pump pressure over here is the maximum we could put into this tank. So that's basically what happens. And as we approach that, the volume of airflow through this valve is going to drop off. So that's like our voltage. I'm tracing with my mouse pointer instead of my nice little pen. This is like our voltage, and this is like our current. So wanted to just throw that out there. We also have inductors. And inductors are basically just a coil of wire, and they store energy in a magnetic field. We measure them in henries. I mentioned on one of the previous ones an adjustable one's called a slug. And I'll mention real quick for a capacitor. If I wanted an adjustable capacitor, there's lots of ways I can do that. I can have something where these plates go closer together. I can have, say I've got, pretend this is like a knob with like a metal plate. Suppose I have another metal plate back here, and as I turn the knob, maybe this one goes this way, and parts of the plate cover each other up, and makes a bigger area for the bigger area will end up being more capacitance, or in bigger area there's more places for the charge to collect, so bigger capacitance. So that's one way you can do that. With a wire or with an inductor, lots of ways you can do that. Maybe you've got a tap that runs part of the way down, and as you turn the knob, it basically just slides along here and picks a different spot. That's an adjustable one. Anyway, bottom line is, in general, an inductor is a piece of wire that has a coil to it. And as it turns out, all wires are going to have a little bit of inductance, and they're all going to have a little bit of capacitance, but that's okay. We'll deal with that later on. But why we would use an inductor. Oh, I should go through the equations here. Same sort of thing you can imagine we talked about earlier. If at t equals 0 we close this, we charge this inductor. And so we're generating the same graphs. I'm actually not going to redraw all these graphs. But what I will call to your attention is how the time constant changes. And so just something to keep in mind. So basically, if we want to change the time constant, we can change the resistance value or the inductance. And just a little design note, both on capacitors and inductors. If you have to design a circuit or you have to design some time constant, there's lots and lots and lots of values of resistors and only, well, significantly fewer possible values of inductors and capacitors. So design around your inductor or capacitor first, and then you can fill in with resistances later. Okay. I should also mention really quick, if you combine capacitors, they're exactly opposite of resistors. So if I have capacitors in parallel, you could think of that as, one big plate, right? Or one set of big plates. So if we have capacitors in parallel, we add the capacitances. So C equivalent equals C1 plus C2, ... But if I have them in series, they do the 1 over thing, just like resistors would do. So if I have them in series, CE equals 1 over CE equals 1 over C1 plus 1 over C2. So just a side note, they're opposite from resistors in that way. And just to make things convenient for us, because an inductor is really just a coil of wire, their series and parallel combinations behave like resistors. So if I had some circuit, I had an inductor here, and this was 5 henries, and this was 7 henries. Because these are in series, we would add them. So we'd have, basically we could represent that as a 12 Henry inductor. So just a little side note, the parallel combinations work the same way, where it's 1 over L equivalent would be 1 over L1 plus 1 over L2 plus, you get the idea. Okay, I'm not going to go through those drawings again. You get the idea with this. Same sort of thing happens if I open this switch and close this one at time equals 0. We discharge all of this energy through that resistor. So places we might use this, such thing as a solenoid. And if you remember from your physics class, I'm going to draw this, we'll give it a shot. There's our inductor. And I said that we store energy in a magnetic field. Well, if you remember, anytime we run current through a wire, we get a magnetic field. And the neat thing with magnetic fields is if I were to put a piece of metal in there, change colors again. Say I put a piece of metal in there. Run right through the middle of them. And I change the current here into this inductor. That changes the magnetic field and can move this piece of metal. So a couple examples of this: when you go to start your car and you're turning your key, there is a starter solenoid. Basically, you dump all of the batteries current. So basically we've got a step, actually like a step voltage across this inductor. We get that, it changes the current quickly, and that forces this metal rod out. And really simplified version would be to have a gear on the end of this. That's a really bad gear, but there it is. And that gear engages with the ring gear that starts your engine. And that's why when you turn the car to start, once the engine starts, you let go of the key and it springs back, and this retracts and isn't just sitting there trying to grind against that gear. Another application is, suppose we have a valve and we've cut away this solenoid. The solenoid's in here. But the idea is we send a signal to it and we change the current. That this piece here and this piece here is the solenoid. But as we change this current, we move this plunger in and out, and this armature in and out. That moves this disc, and we can change the flow through this valve. And solenoid valves are really common. A lot of sprinkler valves are them. You'll use them in industry. It's a really common device because I can just change this. Typically, it's a 4 to 20 milliamp signal, and normally you have some other power source, and you're just using this as your control signal. But anyway, I basically vary between 4 and 20 milliamps, and that's like an industry standard. And I can change the position of this valve and control the fluid flow through there. So it's a really common device. Another neat thing, and if you start thinking about how these things come together, if I'm changing a magnetic field, or if I'm changing the current through here, and that means I'm changing the magnetic field. If I put something, if we know that a change in, if we know a change in I leads to a change in the magnetic field, and then we put another wire nearby, we know that a change in, it should be a delta, change in magnetic field leads to a change in current. So basically, if I change this current, I change the magnetic field nearby, and that can induce a current somewhere else. And that's the idea behind a transformer. And so the deal with a transformer is it's a way to step up a voltage or step down a voltage. So, at the power plant, maybe we take whatever voltage we generate from our turbine, and I'm making up numbers here. I'm totally making up numbers. Say it was 100. Let's say it was 10,000 volts. I step it up to, making up another number, 300,000 volts to transfer it on the high voltage lines. I don't remember this end very well. Anyway, bottom line is, at some point at the top of your telephone pole, wow, just because I can draw doesn't mean I should. Sometimes you'll see a like the cylinder transformers on the top of your telephone pole. And what they do is they take, I want to say this is like 8,300 volts coming along these power lines, and they step it down to like 240 volts for your house. But as we step down the voltage, we have to step up the current. We're not creating or destroying power. So that's something to keep in mind. Another example is your cell phone. You got 120 volt, you plug it in, you plug the wall wart into the wall and it's 120 volts, but then we step it down to 5 volts. And that's all done through the magic of transformers. And I'll talk about this later on in the semester. The most important part, though, of a transformer is this part right here that I've managed to cross out instead of circle. And that is that no electron travels between these two things. So any electron that exists over on this side never makes it over here. And that leads us to build this thing called an isolation transformer. And when I talk about noise and when I talk about some other things coming up in a couple of weeks, I will talk about isolation and why that's important in your instrumentation system. So other than that, there's just some other components. I didn't actually assign a whole lot of homework on capacitors and inductors. I figure if you really want to know about those, you can take a real electronics course. But I did want to mention them to you. So there you have it.